Here we go with section 9.2. This is a continuation of last day. This time we're going to analyze rational functions. Last day we looked at graphs of rational functions that had vertical asymptotes, and also horizontal ones, of course. We found that the vertical asymptote of the graph of any rational function was always found by looking where? Well, if you remember, it was looking at the non-permissible values from the equation, right? The denominator set it equal to 0. However, not all non-permissible values result in actual vertical asymptotes. As you'll see today, sometimes a non-permissible value instead gives what we call a point discontinuity. Point, right? Dot, discontinuity, a break in the graph. Sometimes we call this a hole. Right? Now, when does this happen? Well, this happens in a rational function graph when its function can be simplified by dividing the numerator and the denominator by a common factor that includes the variable. So, example number 1 will be an example of this. So, what do I mean by a common factor in the numerator and the denominator? Well, if you look at example number 1, I'm going to ask you to factor this equation. And if we do, we have y equals to, now on the top, I think we're finding two numbers that multiply to 8 and add to -6. That would be, yes, -4 and -2. And now, can you see why I said there's a common factor? Many of you will be like, oh yeah, goodbye, goodbye. And therefore, y can be simplified to x minus 2. But wait, we have to make sure that we also take into account that factor that we canceled out. And yeah, x can't be equal to 4. Okay? Now, why do I have to include this? I'll show you in 2 secs. Okay? I'm going to ask you to graph out this simplified function. Alright? If we actually graphed out this simplified function, y equals x minus 2, well, that's just like grade 10 stuff now. It's a straight line, y-intercept's 2, slope is 1, easy. Okay? So graph it out. And let's just confirm this with our table of values. We're going to subtract 2 off of all the x values. So 1.5, 1.9, 1.99, 1.999. What happens at actually 4? Well, once again, if I plug in 4 into the expression, it should give me the y value of 2. But remember, I'm looking at the original rational function. So when I plug in 4 into the original rational function, you get undefined. And that's, ladies and gentlemen, why we have to include this thing, where x can't be equal to 4. Okay? 4.001 is 5. If I plug it in, I believe we get 2.001, 2.01, 2.1, 2.5. Okay? Plugging it all into the original rational function. Now, using this table of values, my graph here in red is wrong. Because at 4, it's actually undefined. Now, notice when I get closer and closer to 4, now think back to last day if you did calculus stuff, this stuff here is like the limit as x approaches to 4 from the left. And the function seems to get closer and closer to the value of 2. Same thing over here from the right. The limit as x approaches to 4 from the right seems also to be equal to 2. However, at 4, okay, f of 4, the answer is undefined. So therefore, how do I show that on my graph? Well, I show that with an open dot. So let me erase the graph. Let me now put an open dot, or what I call a point discontinuity, at where x equals to 4, so right about here. And then I want to graph it out like this, okay? Straight line everywhere else, except at that point. This point 4, comma 2 is the point discontinuity. All right. So my question to you is, well, how do we know then if we have a point discontinuity or an asymptote? Well, hopefully this will help you out. You have a point discontinuity if the numerator and denominator have at least one common factor between them. Okay, usually it's just one, but there could be more. And to find this point discontinuity, you have to set the common factor to 0 and solve for x. So it's that canceled term, that canceled factor that tells me the point discontinuity. And then, to find the actual y value for the point, you're going to sub in the x value into the simplified expression. Not the original one, because if you plug it into the original one, you're going to get undefined. But if you plug it into the simplified one, you'll find the y value. Okay, so that's the point discontinuity. How do you see if you have an asymptote? Well, that's where the numerator and denominator do not have a common factor. Okay, do not. And to find it, you look for the non-permissible values of the function, set it equal to 0, and that's what we did last day. Okay? Now, it's not an either-or thing. If a rational expression remains after removing the common factors, there may be both a point of discontinuity and vertical asymptotes. And we'll see an example like that later on. Okay? Let's turn the page and let's deal with some more interesting rational functions. Okay, I'd like you to graph these two functions now, and I want you to see if there's any differences between the two graphs. So I will do my colors of blue and red. Let's do the blue one first, and I'm going to ask you to see if you can graph this out. Always see if you can factor first. And I believe you can factor an x from the numerator, so I'm going to do that. And I believe there's a 2 from the denominator, and I'm going to do that. And lo and behold, I've got a common factor. Goodbye, goodbye. So this simplifies to y equals to x over 2. That's just a line with slope 1/2. So I can plot the points 0, 0, slope 1/2, 1, 2. But before I actually connect the dots, I know from our studies on the previous page that when I cancel out a factor in a rational function, there's a point discontinuity. And where is that point discontinuity? Yeah, at x equals to 2. So therefore, if I'm looking for my y value, I'm going to plug it into my simplified function. 2 over 2 is 1, which makes sense. This is actually an open dot. So let's put a nice open dot there. And now I'll graph it out. Oops, this is supposed to be in blue. Ah! Done. There's y equals to x squared minus 2x all over 2x minus 4. Okay? Point discontinuity. How about the red one? I will also factor again. This time the numerator becomes x plus 2. Denominator is still the same. But is there a common factor? So in this case, we have a vertical asymptote. And our vertical asymptote is actually x equals to 2. So now I'm going to draw a dotted line at x equals to 2. And the rest of the graph might be a little bit more complicated, so that's why I said you might need a graphing calculator. You can always make a table of values if you wish. You can always find the x-intercepts as well. So if you want to find the x-intercepts, you want to let the y value equal to 0. And you're solving. Doesn't matter what's on the bottom. What matters is on the top. I think I touched something. Oops. So what matters is on the top. And so really what we have here is that x equals 0, x equals to negative 2. So here, here. And if you're curious what this looks like, I'm not going to spend too much time graphing it out by hand. I will show you the graphing calculator though. Turn it on. Go to y equals 2. And I'm going to make sure that you put brackets around the numerator, okay? X squared plus 2x. Also bracket the denominator, 2x minus 4. And then graph it out. And you get a graph like this. There's your vertical asymptote. Okay? So, if I were to graph this out, just something like this. And then, ooh, goes down. And over here, it goes up somehow like this. Okay? Very good graph. One has point discontinuity. The other one, vertical asymptotes. Alright, next example, 3. Three has an interesting rational function. It's a trinomial. I'm going to ask you to graph that out and also identify any points of discontinuity or asymptotes. So, let's try. First thing you do, that's right, factor. Factoring the numerator. Two numbers that multiply to negative 6 add to negative 1. How about negative 3 and positive 2? Same thing with the bottom. Two numbers that multiply to negative 2 add to 1. How about x plus 2 and x minus 1? Ah, common factor. Bam, bam. Y equals to x minus 3, x minus 1. But x can't be equal to negative 2. This is a point discontinuity. Common factor. If I want to find the corresponding y value, just plug it back into your simplified expression. Negative 2 minus 3, negative 2 minus 1. How about negative 5 over negative 3, or 5 over 3? Negative 2, 5/3. Point right there. Okay. Now how do you graph out the rest of this? Well, you should know there's a vertical asymptote now. Where is the vertical asymptote? Oh yeah. It's at x equals to 1, so we'll graph that out. What about the rest of the graph? Remember how last day I asked you to try to write in that nice format some number over a linear factor plus a number like this? Because it was so much easier to graph out if it looked like this. Remember how we made it look like that? Yeah, long division. So, let's do the same thing here. Okay. Hope you remember how to do long division. Remember, chapter 3 is where we learned it the first time. X goes into X how many times? Oh yeah, in this case once. There's X minus 1. We want to subtract. Take away the X's, they're gone. Negative 3 take away negative 1 is negative 2. So this just becomes 1 minus 2 over X minus 1. Or, if I want to write it nicer, Y equals to negative 2 over X minus 1 plus 1. Well, that's easy now, because we know our vertical asymptote is minus 1, but now I figured out from that last number, my horizontal asymptote is also equal to 1. And the rest should be history. You can make a table of values if you want, but since I know that that point is there, and I guess it might go like this and go up. Over here it must go flat, and probably something down here. Okay. Done. Oh, by the way, I could get this more accurate too. I should be able to find the x-intercepts, right? How do I find the x-intercept? You let y equal 0. So if I use my simplified expression here, and I made y equal 0, 0 equals to x minus 3, x minus 1. Who cares about the denominator? Just make the numerator equal 0. Oh yeah, x equals 3. My bad. Let me go and modify my graph to make it look like what it should be. Go on and erase. Goodbye. Oops. What? Erase. I want to erase. Erase, erase, erase. I want my x-intercept at 3, so let's make this a little bit more accurate. X-intercept as 3. Okay. That's better. Done. Okay. Let's do some more analyzing on page 3. This time I'm switching it up. I'm giving you the graph. You find the equation. And I've given you a set of hints here too, right? It says start by looking at figuring out what factors need to be part of this rational function, right? So build up the factors. Look at where the asymptotes are. Look at the point discontinuity. Look at the x-intercepts, and then you can probably build your function. Okay. What about the asymptotes? Yeah, we see one right away. We see a vertical asymptote at x equal to negative 1. Now that means you have the factor of x plus 1 in the denominator. Okay. Now, how about the point of discontinuity? Oh yeah. I see a point of discontinuity at x equals to 3. So what factor produces that point of discontinuity at x equals to 3? Oh yeah, it's x minus 3. So this factor is in both the numerator and denominator because it has to cancel out or divide out. The x-intercept, where's that? Oh, the x-intercept is at x equals -7. So therefore that must give you the factor x plus 7. Now where does this go? Numerator or denominator? Yes, numerator is where we get our x-intercepts. And I'd like us now to try to build this equation now. If you can, please, really quickly. Think about what you need on the numerator. Think about what you need on the denominator. And I'd like you to create the equation. Numerator x plus 7, x minus 3, x plus 1 in the denominator, and also a x minus 3. All right. You can expand this out. So we have your x squared plus 4x minus 21, x squared minus 2x minus 3, and you're done. You can always double check by plugging in some points, like this one or this one, and it should work. All right? Cool. And last but not least, here I want you to do some matching. Given you 3 rational equations, I want you to match them to the graphs below. Now, I'm going to ask you, please, when you do all these type of questions, to always see if you can simplify or rewrite the equations in factored form. Factored form helps because it helps you find the asymptotes. If you see a common one, it helps you show that there's a point discontinuity. And the numerators always give you the zeros. Okay? So please, factor A, B, and C. And after factoring, compare with graph 1, 2, and 3. And let's see which one works. Okay? I want you to try this, so please stop tape. Try it, then come back and check your answers. Okay? And that's it for today. So go ahead, please, and try this. Don't, once again, be lazy. Alright, I think I gave you enough descriptions. You should be able to match up the graphs. If you still can't, come find me in class and I'll let you know what it is. Okay? Alright. Hope you had fun.